So this is the ice package. This is the warm-up. If you want to do these 3 systems, you can. But in the interest of time, we're going to go through. We've done those 8 to 10 practice problems. Okay, so up until now, for your K constant, whenever you had to find the value of the K constant, the warm-up questions you just did, you were given the equilibrium constants. But if you can imagine, in the lab, it is going to be uber difficult to find 3 concentrations of 3 different things in one flask full of gas. Don't you think? So these are quite difficult to find out in order to plug them into the expression to find your K constant. However, this is known. I know how much I put in because I put it in. I know how many grams I dissolved in that flask of 1 liter, so I know how many moles per liter I have in my flask. But the equilibrium concentrations, which is a whole mixture of 3 different things, is really hard to discover. So this is quite forced and false. This is far more real. So if they give you this, you can easily solve the K value. But more often in the world of chemistry, we have this. And in order to use these values, what I put in first, and still find my K value, I have to use what's called an ICE table. So ICE table stands for initial change and equilibrium. Okay? So let's just read this equation. Let's just read this problem together. And remember, for every reaction, you have a different equilibrium, and at a different temperature, there's a different K constant as well. So, a student puts in 7.71 moles of this alcohol. Okay, everybody get it? Do you know how they can do that? A mass divided by a big M. They know how many moles they put into the flask. They also know that they've got this many moles of carboxylic acid that they put in the flask. Okay, and then they go away for the weekend. And they allow that system to reach equilibrium. So it's going back and forth, but it's constant now. The rates of the concentration, the rates are actually equal. The concentrations remain constant. And they find that the concentration at the end is, the number of moles at the end is 4.80 moles of my ester. Everybody get where I'm going? Equilibrium is established when the total volume is 1 liter, and this is all in a 1 liter flask. Okay, so sometimes some things are easier to find in concentration than others because they're colored, or because they are the gas and the rest is a solution, or because it is a solution, the rest is a gas. So sometimes you can find something. This isn't the case in this reaction, but in other reactions, they are easier to find the concentration of at equilibrium. So I can find one, but not all of them. So here they found one, but not the alcohol concentration, not the carboxylic acid concentration, etc. Okay? So calculate the KEQ, they're going to say. And before you would have said, right, well, KEQ equals, and you would have written an equilibrium concentration. What do I write? Products? What are my products?
The ester water.
Okay, so ester, C2H5COO, C2H5, and my H2O. So products over reactants. My reactants are my alcohol, C2H5OH, and my carboxylic acid. Everybody hear that? And in your warm-up, and yesterday, you went and plugged in these values. Well, if you notice, that's how many moles it is per 1 liter. I have an equilibrium value for that, but not for that, not for that, and not for that. So I can't plug in the numbers and get in my K. I've got to do this ICE table. So what does the textbook tell me, or the question tell me? It tells me initially I have 7.71 moles in my 1 liter flask. So that's given to me. I have 7.37 moles in my 1 liter flask. So that's given to me. And at the end, in equilibrium, I have 4.80 moles per liter in my equilibrium after the weekend. That's how many moles per liter of my ester I have. Okay? Everybody get where I got the red from? Everybody get why I put the red where I put it? Initially, what I started with. I started putting these two in. After equilibrium was reached, I found that. Everybody okay with that? Okay. Initially, did I put any ester in? No, it doesn't say you didn't put any ester in, so therefore you assume no ester went in, which makes sense. Add your alcohol, add your carboxylic acid, get an ester. So here we go, 0 and 0. Initially. It says I've made that much. If I started with 0 and at the end I have 4.8, it must have changed. I need a new color now. It must have changed by an addition of 4.80 moles per liter. Everybody get where I got that change from? Okay, now when you did your esters and you were ripping up paper, for every one ester that you made one water. Right? And if you make, so for every one ester, one water. And if you made 4.8 esters, you would make 4.8 waters. So if I changed by 4.8, I must have also added 4.8 moles of water, moles per liter of water. Okay? So that's your mole ratio. If I make that, I must make that. And for every one ester that you made and you ripped up and you put in the back, for every one of those that you made, you started with 1 carboxylic acid and 1 alcohol. 1 and 1. So if I've made 4.8 esters and stuck them on the back cabinet, I must have started with 4.8, or pardon me, I must have used 4.8 to rip. So I've used 4.8 alcohols, I've used 4.8 carboxylic acids in order to make 4.8 and 4.8. So the change has to do with the mole ratios. That's really uber, I've used the word uber twice, I'm going to stop using it, I don't want to use it anymore. It's very important that you understand that this change column, bless you Nick, that this change column comes from the balanced chemical reaction, the mole ratio. The initial comes from the question, and some of the equilibrium came from the question as well. And then the rest you kind of just fill in the whole table. Okay, so this is a simple subtraction. If I started with 7.71 and I've used up 4.80, then I must have solved 2.91 moles per liter left over at equilibrium. If I start with 7.37 and I'm using up 4.8 at equilibrium, 2.51 moles per liter is what I'm going to have at equilibrium. Good morning, Gabby. Good vite.
I can't walk that fast. I just had 26 shots in my back.
Would you like another one?
Yes.
All right, and now I'm making 4.8 of that too because 0 plus 4.8. Okay, you all right, Gab? Can you be here? Can you be here fully?
Yes.
All right then. Okay, everybody with me? Everybody get that the red came from the question. The green comes from my mole ratio. And the first screen I solved was this one because I had this and I had this. And then I can fill in the rest of the greens through some math and mole ratios. And then the equilibrium concentration, the black, comes from the subtraction or addition. What I started with, how much it changed by, therefore, what I have at equilibrium. Everybody get these iced? Yes, Nick?
So, are the products always going to be like addition, and then the reaction is going to be subtraction?
Yes. I say this in hesitation because I can be talking about the other way too.
Yeah.
So I could say to you, hey, da da la 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 la. A student adds an ester And at the end of the weekend, she finds this is made. Well, now I'm going to be using up my ester. Okay? So you have to, because then I'm actually talking about it this way, aren't I?
Yeah.
Okay, so you just have to be a bit careful about the reading. It's a little bit of a, you know, reading comprehension. Right? Okay. All right. And then it's back to yesterday. So there's my expression. I then plug in my values, where here are my product values, here are my reactant values. All the units cancel out, moles per liter, top and bottom. And so I end up with 3.08, no units, nothing, 3.08. Okay?
Yeah.
Want to ask something?
No, I'm good.
Okay, Nika's not.
No, she's saying like.
I just said something and then I confused him.
But she's saying if it's even if it's a negative here, and you subtract a negative, it's positive. Which makes sense.
I know how I'm thinking of it, and he didn't get it. So
I thought she was saying there's gonna be like a negative.
I'm just going to keep going.
Yeah.
Okay. Okay. Okay, then it says products are favored. What does that mean? And how did they know? What does it mean that products are favored?
There's more product concentration negative right there.
Right, in the end of the equilibrium, I have more products than I do of reactants. Or if I was redrawing these arrows, I could draw that big and this little. More products than I have reactants. How do they know that, besides the actual numbers? How do they know that based on the K value?
It will be larger.
The K value is a large value. Remember those small ones are like times 10 to the power negative 5? Okay, so it's a large K value. If that's a large number, then this is a large number, and these are my products. Big over small is a big number. You were here yesterday, weren't you, Burke? Yeah, okay. Okay, everybody okay with that? So products are favored means that the concentration of products is greater than the concentration of reactants. That's what that means. How did I know that? Because in order to have a big number here, I have to have big over little. Right? Simple, like, fractions. You don't need to write any of that down, Samantha? To keep yourself engaged?
I did.
Okay? Okay. So then I've got some steps here for you. Write the chemical equation. Set up your ICE table with the columns. Fill them in. Write your K expression. Plug in the numbers and units. And answer with units, which will be different every time. Okay, so let's try some. Question 1. Let's just read question 1 together first. For the system, A plus 2B gives me 2C. The following concentrations are found in equilibrium. A, B, C. Calculate the K. Does this require an ICE table? No, this is like yesterday. Everybody get that that doesn't require an ICE table. I've just got the numbers, I plug them into my expression, done. It's okay, Gabby. Oh, you want a paper probably, hey? Yeah. Here you go. Should ask. Okay, so let's move to 2 because 2 is an ICE table. So I'm just going to skip over 1 in the interest of time. And we're going to do 2 together. All right, so first step was to write that down, right? So A plus 2B arrows 2C. Then I'm going to write ICE, initial change equilibrium. I'm going to put a line between my C and E because that will remind me to add and subtract those 2 numbers to get an answer. That line from grade 2 or whatever, right? Where we love that line. Makes us feel comfortable and secure. It's true though. Okay, what information is given to us? 1 mole of A and 2 moles of B were placed in a 1 liter. Oh yeah, that volume thing. These have to be concentration. As soon as I recognize it, I'm going to write it down. 1 mole per liter, 2 moles per liter, so that I don't mix it up. If it was per 4 liters, I'd write in 4 liters and I'd change it right there. as soon as you recognize that volume, you've got to put it in. Otherwise you make a mistake and you start putting moles in there, and then Samantha says, it's in 4 liters, and everybody has to get out their erasers.
So you don't have to change like the initial, like the 1 or 2 or anything, you just have to put per liters, or like per 4 liters, for example.
Yeah, because it's in 1 liter.
Okay.
Now, if it was in a 4-liter flask, like question 10 of your warm-up was,
Yeah.
then I'd have to go over here and say 1 divided by 4 liters. So that's actually 0.25 moles per liter.
Okay, but should
And this
we?
is and then I plug that, 0.25,
Okay, okay,
in here.
alright,
This is just like an N divided by V.
alright.
C equals N divided by V.
Okay.
If you love your formulas. Right? That's what you did for question 10, right?
No, that's what I got it wrong.
Okay, yeah, that's what you need to do for question 10. You have to divide everything by 4 because you need concentrations. Okay, so that's not 4, that's 1, and that's not 0.5, that's what? Okay. So 1 mole per liter of A, so those are my initials, right? Lots of colors here. What color was I think it was red. So 1.00 moles per liter for A initially, and initially 2.00 moles for B. What other information can I get out of my paragraph?
The concentration of A was found to be like 50 moles per
The
liter.
equilibrium.
At equilibrium. So at equilibrium, A is 0.50 moles per liter. Okay, does everybody understand where I'm getting my red numbers from? Gabby? Okay. So, now I can start filling in my changes. How much did A change by? 0.5. Added or subtracted?
Subtract.
Right. B, am I going to add or subtract B?
Subtract.
Subtract, I'm going to use it up. If I've started with it, I'm going to use it up. How much B am I going to use up? 1, very good. How did you solve for that?
Because of the 2 in front of the B.
Right, if it's a 1 to 2 ratio, then it's a 0.5 to 1. Or for those of you that use this in Chem 20, multiply where you're going, divide where you've been. So 0.5 times 2 divided by 1, if you need to use that still. Okay? So 0.5 to 1 if it's a 1 to 2 ratio. How much would C have changed by? 1, because it's also a 1 to 2, or 2 to 2 is 1 to 1. So this is 1.0. Am I adding or subtracting C? Am I making or using up? I'm making it. How much did I start with of C? 0, because it doesn't say. Therefore, I assume not. Everybody happy with the blues? Gabby, did you get where I got the blues from? Okay, so if I've started with 1 and I ended at equilibrium with 0.5, I must have used up 0.5. Okay? Now remember when we're building our Lego? And if I need 1 bag of red for every 2 bags of blue, and I get 2 airplanes built. So here I don't have 1 bag of red, I only have 0.5 bags of red. So I only need 1 bag of blue, therefore I'm making 1 airplane, not 2. Okay, remember that mole ratio. Okay, so now I can solve for the equilibrium concentrations of everything, because now I love this grade 2 math, where I have 2 minus 1 is equal to 1, and 0 plus 1 is 1 moles per liter. So what are the equilibrium concentrations of B and C? Well, B is there and C is there at equilibrium. Okay? And this is more likely in the lab. I know I've added, I know I've added. I know I didn't add. And at the end of the day, there's probably one I can find the concentration for quite easily, and then I do my math to figure out the rest in this ice table. Okay, so what's the value of K? Well, like yesterday, I need to write an expression. So K equals C squared over concentration of A times the concentration of B squared. So this is 1 squared divided by 0.5, oops, that's a messy 5, times 1 squared. My 1 squareds cancel out. I've got 1 divided by 0.5, so that's a lovely number 2. Which is a big number, therefore my products are favored. Units? Not quite. Liters per mole. My moles per liter squared will cancel out my moles per liter squared, and I'll be left with 1 divided by moles per liter, which is 1 divided by a fraction is the reciprocal of that fraction, so liters per mole. Or 1 divided by 2 over 3 is equal to 3 over 2. If you don't believe me, or if you forget in a test, just type in 3 different numbers in your calculator. Make sure this is in brackets. Hit answer, and you'll get 1.5. Okay? If you forget. Right. Questions on that? Okay, so let's, 3 is like yesterday, 4 is like yesterday. Let's scroll down a little more. 5, 6. Let's do 7 and 8. Oh yeah, I've written my table on it for me. That's quite nice for myself. Okay, so let's do 7 together then. The answers to all of these will be on Moodle, so therefore you can check your answers if you go back and do 6, 5. Oh, I even put them in the back of your package. Look at that. Okay. All right, so for question 7, I'm going to let you get started, but it's got a bit of a twist to it, okay? So you go ahead and get started, and when you get stuck, I will know. So Gabby, the first thing you're going to do is you're going to write the balanced chemical equation and then write ice. Are you stuck here? Did you get that much done? Yes, yes, no, yes, yes, yes. Okay. And this is where you probably should get stuck. Okay? Because I don't have anything to kind of change on my table. I don't know any of the equilibriums. I don't know any of the changes. I know the ratio is 1 to 1 to 2. but I don't know what it is that's changing. Here's my K value, but I can't just plug in X for these and solve for X, which might have been like your default setting. Did anybody think about, oh, I should just try that? It's a good thought. Except for what you're saying then is they all change by exactly the same amount. They don't. And the equilibrium will be the same amount, but it won't be, because I started with more of one. So this is what you have to do. If this changes by a certain amount, then this will change by
So,
the same amount. So I'm going to call that X as well. And this will change by,
2x.
right. Which means at equilibrium, this value will be,
175 subtract x.
right, oh, I should have put those, I'm going to take those away and I'm going to add that, right? And this value will be the same. And this value will be
0.75
just 2x. 0 plus 2x is 2x. Okay, just down the column, grade 2 style, only with x's. Now I've got some numbers, or some e's anyway, that I can plug into here. So now I have 49 equals, hi is, at equilibrium is 2x, and that's all squared, because hi is squared. At the bottom, my h2 is 0.75 minus x,
Can you just square that?
and I am going to square it for simplicity. So because h and I are the same concentrations, I can then just put squared. And the reason I want to do that is because I, in chemistry, do not want to solve a quadratic equation. You know where you have a certain number of x squared minus something or other x plus a number. Do you know what I mean? You'd have to solve the, negative b plus or minus square root of, remember that? Yeah. It's in your data booklet if you ever need it, negative b plus or minus square root of b. But for the, with 2 weeks left to cover the curriculum, we are not going to solve any quadratic equations, because you will not face one on the diploma. Okay? But by the time you get to organic chemistry, or not, this is not organic chemistry, but anyway, by the time you get to year 1 chemistry in university, they'll expect you to be able to solve quadratics and be able to apply that here. So if we had a bit more space, a bit more time, we'd do a couple, just to say, yes, we can do this. But we don't, so we're not. Okay? So you will never face a quadratic, is what I'm trying to say to you. Not on purpose. I might give you an example and not realize it was but not on a test, and not on a. Right, so how can we get rid of these squareds so that we don't have x squared? I can square root both sides. Da-da-da, da-da-da, boom, gone. So then I have 7 equals 2x over 0.75 minus x. Hurrah, x squared's gone. I'm going to take both sides and multiply that by 0.75, right? So 7 times 0.75 minus x is equal to 2x. Then I'm going to take that 7 and I'm going to multiply, somebody borrowed my calculator. No, thank you. I'm going to take that 7 and multiply it out. So 7 times 0.75 equals 5.25 minus 7x equals 2x. So 5.25 is equal to 9x. And so divided by 9, oh, quit, it says, I don't know why. 5.29. X equals 0.583 repeating, but I only have 2 significant digits, so done. And at this point, the mathematician in you goes, woohoo, done, circle the answer, move on. But the chemist in you should go, no, I'm not solving for X, I'm applying this concept. So what was I actually trying to find? The equilibrium concentrations of H2, I2, and HI. Have I found that? Not yet. I've got to take that value and plug it in order to find my concentrations. So, have I given you back my calculator? That was pretty dumb. Okay, so 0.75 minus 0.85 is, just gonna have a sneaky peek at the answer key so I don't have to then grab the calculator again. 0.71, oh pardon me, 17 moles per liter. This will be the same. And 2 times 0.58 is 1.17 moles per liter. And now I'm done. And, ooh, answer. Okay, so don't stop at X, like you think, because it's a big effort, and you're like, hurrah, move on. No, it's, you gotta keep going. Okay, get it? Okay, I'm gonna change question 6 slightly. Do you see here 0.4 and 0.4? So in your packages that you have, can you please change that? So now it's 0.4 moles per liter here. Just to make sure you don't, otherwise you have to solve a quadratic. Okay? Now, this question is exactly the same as this question. So you're going to do this question. Do you want the answers? So that because they're different from what's on the back of your sheet. The new answers are the H2 and the I2 concentrations will be equal, and they will equal 0.088 moles per liter, and the HI concentration is 0.62 moles per liter. That's it. That's a double 8. It's a messy one, but it is one. Okay, so try this to see if you can do it again. Then we've got some practice problems here, just 3 of them, which then hopefully will take us 15 minutes less 3, and in the last 3 minutes I can explain to you what your weekend homework is, which is quite simple. Questions? So you have 4 questions to do right now.